All right, if you've ever built a neural network, trained in embedding, or honestly just wrestled with PyTorch for an afternoon, you've used vector norms. Today, we're taking what often feels like abstract math and transforming it into concrete, absolutely indispensable engineering tools. We're going to see exactly how these mathematical rulers dictate the true behavior of our models.
So it all starts with a surprisingly simple, wonderfully human question. How do you actually measure the length of a list of numbers? I mean, we all intuitively know what an arrow in three-dimensional physical space looks like, right? But when that arrow is a 1,000-dimensional embedding vector, measuring its size or its energy becomes remarkably tricky. How much vector there is? Well, that entirely depends on how you choose to measure it.
Okay, let's dive into this. The concepts we're unpacking today act as both the mathematical rulers that measure our vector networks and the leashes that keep them from completely exploding. Without them, we literally can't measure error, we can't stop weights from spiraling out of control, and we can't even compare vectors. They are the absolute foundational infrastructure of distance, constraint, and scale in machine learning. Here's our roadmap for this explainer. We'll start with part 1, rulers of vector spaces. Then 2, the math behind measurement. 3, shapes of norms. 4, norms in ML. And finally, 5, code and catastrophes. Let's get to it.
Section 1. The rulers of vector spaces. Measuring vectors.
Before we touch any calculus, let's build some visual intuition. Imagine you're standing at the corner of 1st Street and 1st Avenue, and you're trying to get to 4th and 5th. The L2 way, the Euclidean way, is kind of like strapping on a jetpack. You just fly in a perfectly straight diagonal line directly to your target, exactly as the crow flies. But the L1 way is entirely different. Imagine you're a taxi in a rigid Manhattan grid. Buildings block your path. You literally have to drive 3 blocks east, then 4 blocks north. The total distance isn't the diagonal, it's the sum of the horizontal and vertical blocks.
Moving on to Section 2, the math behind the measurement, formalizing distance.
Keep those jetpacks and taxis in mind, because these equations are just formalizing those analogies. Back in the 19th century, a mathematician named Hermann Minkowski realized that distance isn't just an absolute law of nature, it's actually a flexible definition. He formalized this beautiful parent equation, the general LP norm. Notice how changing that little p-value dynamically alters the very geometry of the grid, from squares to diamonds to curved shapes. Let's see what happens when we actually plug different numbers into p.
If we set p equals 1, boom, we get the L1 norm, our Manhattan taxi. It's simply the sum of the absolute values of the vector's components. It treats all magnitudes linearly. And because it doesn't cost extra to have one big component, it makes it mathematically cheaper to just zero out small, useless components. This is exactly what induces sparsity in our models.
Now, if we set p equals 2, we get our classic L2 norm, the Euclidean jetpack. It's the square root of the sum of squared values. Because we're mathematically squaring those components, the L2 norm heavily penalizes large outliers. It prefers vectors where the mass is spread out in a bunch of small, smooth values. And as p approaches infinity, things get wild. We get the L-infinity norm, also known as the Chebyshev norm. Imagine a king on a chessboard moving diagonally. For L-infinity, the smaller components become completely mathematically irrelevant. The entire norm is defined simply by the single largest, most extreme component in the entire vector.
Often in machine learning, we'll actually just strip away the square root entirely, leaving us with the squared L2 norm. Now, actually, scratch that. Technically, this isn't a true mathematical norm because it fails the rule of absolute homogeneity, but avoiding that computationally expensive square root makes it absolutely indispensable for core functions like mean squared error loss and weight decay.
Now, what's really interesting here is the derivative. When we take the derivative of the L2 norm through the chain rule, the gradient ends up being the vector itself divided by its own L2 norm. The result is just a perfectly scaled unit vector pointing exactly in the direction of our original vector.
Section 3. Shapes of norms. Visualizing unit balls as circles, diamonds, and squares. So, what does this all mean geometrically? If we plot these equations on a 2D coordinate system to find where the norm equals exactly 1, we get what are called unit balls. The L2 unit ball forms a perfect, smooth circle with absolutely no corners, which spreads out future importance. The L-infinity ball forms a rigid square. But look at the L1 norm. It forms a diamond with incredibly sharp corners sitting right on the axes. This right here is the secret of sparsity.
When an optimizer is trying to find the lowest loss intersecting with this L1 diamond, it almost always hits those sharp corners first. And because the corners are right on the axes, it means one of the coordinates is forced to be exactly 0.
All right, Section 4, Norms and ML, Real-World Architectures. Let's see how these rulers act as leashes in practice.
Take gradient clipping, an absolute lifesaver in reinforcement learning and transformers. Let's walk through it. If our gradient vector is 12 and 5, step 1 is to compute its L2 norm, which gives us 13. Step 2, we check if 13 is greater than our safe threshold, say 5.0. It definitely is. So step 3, we scale the entire vector down by multiplying it by 5 divided by 13. The result? We get a new gradient pointing in the exact same direction, but safely capped at a magnitude of exactly 5.0. That L2 leash literally stops the gradients from exploding.
We see this leash acting as an unbreakable chain in transformers with layer norm. Notice the variance term in the equation sigma squared. It is fundamentally proportional to the squared L2 norm of the mean-centered vector. By literally dividing the activations by their own L2 norm, layer norm guarantees that the signals passing through your deep transformer layers remain perfectly stable and never violently explode. And finally, Section 5, Code, Compute, and Catastrophes, Implementation Pitfalls.
Because mathematical ideals don't always translate perfectly to silicon, right? Choosing the wrong norm or coding it poorly will silently break your architecture. If you call torch.norm on a batch but forget the dim equals 1 argument, you normalize the entire batch as one giant vector instead of per sample, creating total garbage. If you forget to L2 normalize your embeddings in contrastive learning, your model just cheats by making vectors longer instead of actually learning semantic angles. If you use pure L1 loss for object detection bounding boxes, that sharp corner at 0 causes the gradients to oscillate wildly. These are silent, architecture-killing bugs.
And this brilliantly illustrates why you should never write your own raw sum of squares function in production. Think about it. If a value is 10 to the 20th power, squaring it results in 10 to the 40th, which instantly overflows standard float32 memory and throws a nan, not a number error. To compute this stably, engines like PyTorch first find the maximum value, m, and divide everything by m before squaring. This guarantees the largest term is exactly 1.0, safely preventing numerical overflow under the hood.
To bring it all together, think of how these leashes actually feel to the network. The L2 leash pulls weights gently, kind of like an elastic band. It never quite hits 0, it just keeps things small and distributed. But the L1 leash, it's like razor wire. It aggressively snaps unimportant feature weights exactly to 0, forcing the network to select only the absolutely most vital information.
If you take away literally just one concept to permanently embed in your engineering toolkit today, let it be this. L1 makes zeros, L2 makes small things. Normalization shrinks arrows to length 1, and norms are the leashes that keep neural networks from exploding.
But I want to leave you with a fascinating open question currently being explored in AI research. We've treated the p in the Minkowski equation as a fixed choice, either a 1 or a 2. But what if we made p a learnable parameter? What if the network could dynamically interpolate between the razor wire of L1 and the elastic band of L2 during training, perfectly adapting to the sparsity it needs on the fly? The mathematics of vector spaces are still evolving, and understanding these rulers gives you the power to shape that future. Thanks for joining me on this explainer, and I'll catch you next time.